Hello, everyone. Welcome to another great session of our ExpoLab blockchain speaker series. So today is a great pleasure to have Xinying joining us, and he's joining us from China. And so he is the founder and the chief architect of LedgerDB by Alibaba and Financial Group. And so he had a very interesting career. He was at IBM. He's even won the China corporate elite under 40, which is I think very similar to the Forbes 40 under 40 I think award, which is a very prestigious. And so we're very excited to have Jerry. And so with that, please take it away.
So hello everybody, this is Derry here. It's a great honor for being invited by Professor Mohammed to share our technology and product. Nice to meet all of you. We propose a new term called centralized ledger database for this emergent blockchain database branch, and developed LedgerDB, which is now available and is supporting global customers on Alibaba Cloud. Okay. First of all, we still have to interpret some terminologies in my presentation. We are all familiar with DLT, so I'm not going to talk about it much. CLT is an emergent branch in Ledger Technologies, and we propose a new term called Centralized Ledger Database, CLD, which belongs to CLT, Centralized Ledger Technology. LedgerDB, Amazon QLDB, Oracle with blockchain table, and Proven DB all belong to this kind of database. Next, we have to differentiate immutability with tamper resistance. Immutability is a characteristic, a rule, but tamper resistance is a systematic capability. Auditability is a serial of verifications based on predefined rules. Internal audit ensures that an internal user of the ledger can observe and verify the authenticity of all actions conducted by all other distrusted users. For example, a traditional audit table in DBMS can satisfy an internal audit because DBA can audit all users' historical log trials. An external audit is for an external third party to observe and verify the authenticity of all actions. So traditional audit table doesn't satisfy this request. A third party can't trust the audit log because DBA can tamper data. We all know that. Okay, so in this section, let's go through the history of database world. We all know that after Core publishing the paper of relational data model, DBMS comes to a new era. Traditional OLTP DBMS like Oracle and DB2 have some functionalities of security and audit, like security labels, role permission, column masks for data privacy, and also audit table for auditing. But they all have a prerequisite that DBAs are fully trusted, meaning that they don't have malicious actions. But in reality, DBA can change a certain transaction log to change digital history by insertion, updating, and deletion. They can also fabricate an internal timestamp within the database, so it is very easy for them to be evil. And these kinds of defects obviously make traditional DBMS lack of judicial level credibility. The same situation happens to cloud DBMS and traditional NoSQL systems. We all know that the emergence of blockchain has attracted widespread attention, especially for their cryptocurrency prices. Bitcoin is the first blockchain system by implementing a hash-linked transactions method and the proof of work consensus paradigm over a public network that anyone can join. It is highly decentralized and widely spread. but its throughput is very low, and it has too many replicas. We all know that. For permission blockchains that claim to use in enterprise collaborative applications, we observe that many real applications on permission blockchain don't benefit from the decentralized architecture. But the blockchain architecture, like multiple peers consensus, limits its throughput and increase storage overhead. What is worse, although its mechanism seems credible, but its lack of rigorous credibility and auditability. We'll talk about this later. So why CLD is important and valuable? We all know that many applications deploy on their blockchain nodes on a bus, blockchain as a service environment, maintained by a single service provider like Alibaba Cloud or Amazon AWS. This forms a centralized paradigm rather than a decentralized manner. Besides this characteristic, permission blockchain and current CLD systems are also not highly performed with storage overhead and has regulatory issues and limited external auditability. Below is the forecast trend data from Gartner. From the estimation, we can see they enlarge the replaced percentage from permission blockchain to CLD system from last year's 20% up to more than 50%. If this really happens, that would be a revolution in blockchain applications. In our practice, more and more blockchain customers like intellectual property protection, data lineage applications, and supply chain finance on Alibaba Cloud are switching to our product. Okay, so LedgerDB is a ledger database that provides temporary evidence and non-repudiation features in a centralized manner, which realize strong auditability, high performance, and data removal. Let's see the key comparisons between LedgerDB and other systems. We can see LedgerDB provides the highest performance among these ledger systems. Regarding external auditability, LedgerDB can achieve permissionless blockchain, like Factom's credibility. We realize credible timestamp by pegging with TSA, while Factom use Bitcoin by one-way peg. We pointed out that QLDB and Fabric are lack of external auditability because their threat model makes the consortium or ledger service provider can fabricate timestamp so as to fork a different ledger to cheat an external auditor. We also support purge and occult operations, which break traditional blockchain's immutability. After we investigate real-world customer requests, they often want to delete historical data when not affecting recent data's integrity checking. This is a motivation of purge. And illegal information should obviously be hidden, which is a motivation for occult. We also support both client and server side non-repudiation and efficient native lineage insertion, retrieval, and verification. Okay, and this slides illustrate how LedgerDB works. This figure can also be found on our official website on Alibaba Cloud. This workflow depicts LedgerDB Xinying framework, which will also be discussed later. You can see step 1 submits a user request. Then step 2 stands for Ledger proxy dispatches job to Ledger server. Then step 3 is how Ledger server records data and then respond back after signing in step 4. Step 5 describes how to interact with TSA using Time Ledger as a public service. This is the chief protocol for external auditability. This is our architecture of data and control flow. Ledger client submit job to Ledger proxy. Ledger proxy receive client request and then dispatch them to the relevant server. Ledger server then complete the final processing of request and interact with bottom storage layer containing L stream, KB store, MPT, and HDFS. L stream is our designed linear structured append-only file system. Okay, this is our operators and main APIs in LedgerDB. Append API is used to append user transaction or system-generated transaction to Ledger, involving insert transactions, set trusted anchors, grant rule, and TSA timestamp. Receive API gets qualified journals from Ledger based on JSN, journal sequence number, clue, trusted anchor, and TSA timestamp can also be fetched using relative API. Verify interface is used to verify integrity and authenticity of returned journals from journal proofs based on journal sequence number or clue. Create is used to create a new ledger with initial roles and members. Purge removes obsolete journals from ledger and occult hides journal from the ledger. Recall API is used to roll back a purge within a limited time window, and delete is used to remove entities in the system, such as a ledger, a role, a member, or a clue. We can see the Xinying workflow on the data structure figure. This workflow makes none of client and LSP can repudiate. At client side, a journal is initially packed as a payload called journal data, which contains operator-related and client-related fields. Request hash is computed based on the entire journal data. At server side, the journal structure is called server journal. JSN, stream offset, server timestamp, and execution receipt are all finalized. The server then calculates the journal hash. After a journal is committed, the server returns a journal receipt to the client, including the final block hash. We implement a three-phase transaction management. The first is the execute case run on Ledger proxy for better scalability. A transaction enters this phase based on the transaction tag. The commit phase runs on Ledger server. It collects multiple executed transactions, arrange them in a unique global order. We call it general sequence number, we mentioned before, and permits them to the storage system. The last index phase is to build indexes for data retrieval and verification. In particular, we have three types of indexes here. They are clue index, BAMT accumulator, and block information. Yeah. Our strong external auditability leverages the two-way PEG protocol involving TSA journals. TSA stands for Timestamp Authority, which provides credible timestamps. A TSA journal contains a submitted digest and a credible timestamp sent by TSA. These journals are entangled between each other to form a time clue. A ledger digest is firstly submitted and then sent by TSA, and TSA journal is then recorded back onto Ledger as a TSA journal. We offer T-Ledger service that can sustain much higher throughput on Alibaba Cloud. A time ledger can be maintained by LSP as a shared time notary service for common ledgers. It accepts a digest submitted from different ledgers and interact with TSA. It acts as an agent between common ledgers and TSA. Okay, This slide summarizes the multi-party signatures that ensures LedgerDB non-repudiation. We can see the user sends before it's submitted to a Ledger service. LedgerDB sends the receipt when respond to user, and TSA sends on Tsa journals. Okay, let's talk about the verifiable data removal. LedgerDB supports several data removal operators demanded by real-world customers. It breaks immutability in conventional blockchain, but still preserves verifiability. We know that in traditional blockchains, once the data is written onto ledger, it cannot be deleted or modified. But this leads to prohibitive storage overhead and regulatory issues in real-world applications. Many blockchain users want to clean up historical records to save storage. Purge resolves this customer request. A purge operation deletes a set of contiguous journals dating from Genesis or latest pseudogenesis to certain specified GSM. This SQL interprets the purge operation. We can see that all journals before purge GSM are erased from the ledger. Another defect is traditional blockchain's immutability is the regulatory issue. Imagine someone upload other people's privacy data without approval, like someone's personal ID card information. This should be deleted in real-world applications. OCULT is designed to support this kind of violated information hiding. An OCULT operation converts the original journal to a new one that only keeps its metadata and retains its digest. From the interpreted SQL, we can see that all the payload data are hidden and filled with its entangled journal GSM, hash, and padding blanks. Okay. We support native lineage by a proposed concept of clue. A clue is a user-specified label that carries on business logic for data provenance. Customer can specify certain clue when inserting data by appending. Fetch certain clues record by clue retrieval and verify a certain clue by clue verification. Here is a merchandise order example of clue usage. Order 1, 2, 3, 4, 5, 6 is the specified clue ID. When customer places the order, journal represents not paid is inserted on ledger. After customer paid, another journal for this information is recorded. Same thing happens when the merchandise is delivered and received. We can see all the corresponding journals for this order can be traced using clue. We design all right optimized clue index structure and dedicated verification protocol combining clue counter MPT for fast clue fetching and verification. Okay. Conventional accumulator calculates root hash for each transaction. This makes CPU cost quite high when data volume is large. We designed the batch accumulated algorithm to calculate a single root hash for a batch of journals when system throughput is high. We can see that the bigger the batch size is, the higher throughput it will be, but the proof granularity will be lower. LedgerDB's clue index is working as designed for write optimization. We can see the write OPS can exceed 1 million, and CCell is also friendly to point read and compared to RocksDB. We can see our experimental data for LedgerDB end-to-end performance from this slides. LedgerDB's write and sequential read throughput can reach more than 300,000 TPS. For real-world applications, we apply a same notarization application on both LedgerDB and Hyperledger Fabric version 1.4. The experimental result shows the LedgerDB is 80 times faster than Fabric. In real applications, there are 3 styles of user scenarios. They are monoledger, federated ledger, and delegated ledger. Monoledger is the simplest style, in which only one peer exists. An example for monoledger is a ledger where everyone keeps his own privacy journals without intersections with others. Federated ledger has more than one participant who had the demand for a mutual audit. We have a supply chain customer that use LedgerDB to provide tamper resistance and mutual repudiation. All related corporation peers such as manufacturers, retailers, suppliers, and warehouses are all certified as members who can append their IOUs, manuscripts, invoice copies, receipts as journals on a ledger. Delegated ledger only interact with a centralized agent who further manages other participants with the demands of mutual audit. A trusted hardware is involved in this solution for delegated signing. An MPC system on Alibaba Cloud use this solution to track their mutual data exchange and SQL manipulations. Details can be found in our paper. Here, we compare a federated ledger with a permission blockchain. LedgerDB can get a higher performance, lower cost, easier usability, and better external auditability in same blockchain applications. The pie figure shows our customer application distribution percentages until August this year. IoT data tracing, insurance, supply chain finance, intellectual property, regtech, retail, healthcare, manufacturing, and energy. A real world happening is that more and more permission blockchain customers are moving forward to CLD systems. Okay, welcome to try LedgerDB on Alibaba Cloud, and email me anytime if you have interest in LedgerDB and wanna contact us. Thank you all again. Thanks.
Thank you so much, Derry, for an excellent overview of insight into LedgerDB. So I guess, do we have any questions from our audience, from the students?
So I have a question. Thank you for the presentation. How much is the replication? How many replicas are there in LedgerDB? In these experiments, how many replicas are you using?
Okay, so the replica is besides common centralized systems. It's about 3 replicas. So yeah, and the for the public cloud, you know that the public cloud service, the storage service itself has the replica technology. So onto the public cloud, we leverage the public cloud storage system as technologies. Yeah.
So because we're talking about blockchain and like, is there any consensus protocol being used right now in LedgerDB, or there is no consensus protocol, or how are the transactions serialized? Is there any protocol, consensus protocol, which is taking care of that?
Sorry, I didn't.
Like in other blockchain applications, there is proof of work or PBFT or proof of stake. Is there any consensus protocol here in LedgerDB?
Yeah, the LedgerDB's replica protocols is just like the ordinary, very ordinary data consistent protocols like Rust, something like that. Yeah, that keep the data consistent among replicas, right?
Okay, yeah, that makes sense.
All right, any other questions? So do you see, so maybe kind of, I kind of understand this, this space, because we've been so far really focused on the permissionless, and then last few lecture, we had presenter from former IBMer, Mohan, and then we had Marco from IBM Research Zurich. The really focus was on Hyperledger and the permission setting. And here at UC Davis, the Resilient DB is also a permission ledger as well too. So kind of understanding the dynamics of the two. So, I mean, our focus is exactly what you kind of nailed as well, is performance, is to really to get over hundreds of thousands of transactions, something that is not really feasible with the other system that you had also noted in your presentation. So from our perspective, so perhaps maybe you can give us maybe a feedback, and sort of maybe you can find a commonality. From our perspective, it's been two things. In order to scale into hundreds of thousands of transactions, actually Suyash is one of my senior PhD students, who's graduating this year, is to look at concurrent consensus as opposed to running a single consensus. What happens if you are able to do parallel consensus, concurrent consensus? There, we see we can reach up to 350,000 transactions per second, scaling up to 91 or so replicas. On the other hand, we're looking at sharding. They're sort of scaling to 500 nodes, 15 countries globally. And if you have the fully sharded system on a partitionable workload, we're sort of peaking at around 1.4 sort of million transactions per second. And sort of some of our recent results. So how do you see kind of the interplay of kind of between LedgerDB or Resilient DB, or between the centralized ledger versus the permission ledger that like Resilient DB is?
So you mean the
for example, do you see any opportunity? For example, do you see any opportunity sort of transferring some of the work that we've done, for example, in Resilient DB, with a kind of incorporating or integrating it into LedgerDB, or vice versa? So how do we kind of, do you see any sort of transfer of technology between these two spaces? And maybe perhaps not just limited to ours, other ones that you've listed, like Oracle Table, for example, or the other technology you kind of noted earlier on.
I heard the Resilient DB before, but didn't see too much details into that. I think for the LedgerDB and the one direction is how do we leverage the more and more traditional centralized systems technologies, and also leverage the blockchain world's characteristics. This is the most important thing to. We all know that the blockchain is the blockchain technology itself is combinations of several sphere technologies, and make up as an initiative thing. So for the this CLD systems, I think the most direction is how to leverage both sides and initiate some creative things, just like blockchain did previously. Yeah.
I see. Very interesting. Do you have any kind of estimate of sort of how fast the CLD market is sort of growing? Perhaps sort of any sort of projection in your view in the coming years, for example?
So you are talking about the CLDs, real customer and applications?
Yeah. So for example, I mean, as you listed, I mean, Oracle is now into this space, Amazon into this space, of course, Alibaba and financials in this space. So major players are now, I guess, trying to offer blockchain-like technology into their traditional ecosystem, traditional centralized, traditional databases. So how do you see kind of, do you see new emerging areas for this market? Do you think it's really going to expand, or do you think it's going to be tailored for specific domains? Sort of, what's your feel on, yeah, I guess on the market, on these new emerging areas?
So for this question, I think it's a interesting question. Yeah, and I think it's just like traditional DBMS. We all know that when OLTP resolve transaction system things, and OLAP resolve some data analytic things, and then the world comes to the more and more data sphere, and we all know that the web data is very large, and then comes to the big data technologies and a lot of NoSQL. So every database technology has its own characteristic and its market, right? And for the permission blockchain and CLD systems, I think they can be coexist for their own characteristics, maybe for quite a long time. In the permission blockchain, if several participants really want to share each node data, and they really do consensus, and this application maybe have some real market value. And for the CLD systems, I think for most permission blockchain applications, like just data notarization and data lineage, and doesn't have the real decentralized and consensus need. So and needs higher throughput, high performance. So for this kind of applications, I think CLD will be a better choice for customers. Like the data lineage, we all know that to store some judicial proofs, yeah, this is already applied in real world application. We all know that in the internet court, we all know that. And for the data lineage, just at the like the example I showed in the presentation, like the supply chain or supply chain finance, that we record a lot of things when a clue is generated, or its merchandise trace can all be recorded on the CLD system. Yeah.
I see. Very interesting.
Something like this. Yeah.
No,
and healthcare data, yeah, manufacturing data, and this IoT data, yeah. We all know that IoT data is large, right? If this IoT world really comes to our reality, and the data will be expanded, so a CLD system may be the better choice, because one thing is the throughput will be high. For the IoT system, throughput will be high. And the other thing is the data is large. Data is large. So for permission or permissionless blockchain, there are too many data replicas there. So there will be a not good choice for very large data.
I see. Very interesting. And so the other, I mean, Alibaba over the last, I guess, 5 or 10 years, they have come up with really impressive set of database technology. One sort of we kind of followed for a while as well was Ocean Vista and its geoscale transaction models and so forth. Do you see any kind of the blockchain technology that you've been developing, the LedgerDB, do you see ever kind of be integrated or be used in Ocean Vista or alike?
So I think I can't answer this question, because this maybe relates to the enterprise strategy. Yeah, but I think we can see this CLD systems, more and more CLD systems happens in the in other enterprises. We all know that the Oracle already have the Oracle blockchain table in their newest release. So I think this trend, I think this is a trend in the all the industry world, I think. So do you think so?
Yeah, so, that seems like a very plausible and exciting new direction. Yeah, for sure.
Yeah.
So, do you have any other questions from Derry? I mean, this is a unique opportunity. We can get real interesting insight from Alibaba and LedgerDB data ecosystem, I guess, in general. All right, so I guess we're kind of getting close to that 5:20 mark. So I guess we're almost on time to finish as well. So again, on behalf of ExpoLab and on behalf of UC Davis, I really want to appreciate taking the time and so giving us this excellent lecture and introducing LedgerDB to everyone. So thank you so much.
You're welcome. Thank you, Mohammed, and thank you all. Thank you, Suyash, and we hope we can have collaborations in the future. Yeah, yeah.
Thank you.
Nice to meet all of you,
yeah.
And have a nice day.
Yeah. Bye.
Thank you so much. Thank you.